So this lecture, we're going to start developing some tools that we can use for determining when a series converges and when it doesn't converge. So this theorem here uh, starts off by assuming that we have a series that we already know converges, right? And if that's the case, then the sequence that makes up the individual terms has to have this property. The limit of as n goes to infinity of a sub n has to equal 0. And intuitively, hopefully, you think about it for a minute, there's some sense to that. If the limit were something else, for example, let's say the limit was 1, then this is saying that beyond a certain point, every one of the individual terms is close to 1. How many terms are there beyond any fixed point in the series? Well, there's infinitely many, right? So the series will be adding up infinitely many numbers that are really close to 1. Yeah, okay, that's going to diverge. So how can we prove this a little more rigorously? Well, we're going to start with the definition. The definition says the sum is equal to the limit of the sequence of partial sums. So what I'm going to do next here is I'm going to take that sequence of partial sums and I'm going to break out the last term. Right? I'm going to take out the a sub n term, write that off to the side, and what's left is the sum of the first n minus 1 terms. So that's s sub n minus 1. All right, now I'm going to use our limit rules. I'm going to split this up. I'm going to make this the sum of the individual limits. Well, the right-hand limit is the one that we're talking about in the theorem, right? So I'm going to kind of leave that one alone and focus on the first limit. Well, that limit, the limit as n goes to infinity of s sub n minus 1, that is also going to be s, right? Ultimately, we're looking at the entire sequence of partial sums, whether I start at n or n minus 1 or n plus 1 for that matter. So if I replace that with s, I get this. And that takes me really to where I need to be. If we subtract s from both sides, we end up with the limit as n goes to infinity of a sub n equals 0. And that's what we needed to show. Okay, so this is one of those situations where we need to be really careful about what the theorem says and what it doesn't. This is not a theorem for determining when a series converges. This theorem tells me if I have a convergent series, then it has this property. Okay, so why are we talking about this then? Right? Well, if we take this conditional statement and we look at what's called its contrapositive, right? If a conditional statement and if then statement is true, then its contrapositive is also true. Right? Well, the contrapositive of this would be if the limit of the individual terms is not equal to 0, then the series does not converge. In other words, it diverges. So rather than being a test for convergence, this actually gives us a test for divergence. All right, so let's look at some examples here. Right? Say we have this series here. Well, the limit of 2 to the n as n goes to infinity. That's an exponential function. Obviously, that's going off to infinity. It's not going to 0. Therefore, that series is going to diverge. Okay, so how about this one? Right, this is when we got to be a little careful. The limit as n goes to infinity of 1 over n is 0. So what can I conclude based on that? Well, absolutely nothing. This theorem tells us nothing about what happens when the limit is 0. It only tells us what we can expect when it is not equal to 0. When it does equal to 0, all bets are off, could go either way. And in fact, as we'll see in a later lecture, this is an example of what's called a harmonic series. And this one actually does end up diverging. So that's one tool, right, to add to our toolbox. In the next lecture, we're going to take a look at another tool. This one will actually tell us when a sequence does converge rather than diverge. It's what's called the integral test. So there's a link to that lecture down here. And of course, if you like this one, please don't forget to click on the like button as well.